Hi, everybody. This is Mr. Folly, an old country boy, and this is podcast 4.3. I guess it's 5.3. We're going to learn about oxidation numbers, types of reactions, and balancing redox, but just kind of. So, here we go. Oxidation numbers are the charge. So, elements in their standard state have an oxidation number of 0. Remember, oxidation number is charge. O is negative 2, except peroxide. So, an example of a peroxide would be H2O2. Or Na2O2, and there are no other examples of peroxides. And in that peroxide example, oxygen is negative 1. H is plus 1, except when it's with an alkali metal, which would be like NaH, or, well, that's actually the only one, in which case hydrogen would be negative 1. Trust the outside of the periodic table more. So here's a happy, dandy little periodic table. I think I have an example now that I think about it. Oh, nope. So we know in general this is plus 1, plus 2, plus 3, no, yeah, I talked to myself. Plus 3, 0, minus 3, minus 2, minus 1, 0. And something over here is usually minus 2, but doesn't have to be. Like nitrogen has a bunch of different oxidation numbers. And you just kind of have to trust the halogens the most, and alkali metals the most, and go through it. And you'll see in some examples. Like examples. MnO4 negative 2. So I'm going to start off with oxygen being negative 2. So if I have 4 negative 2s, that means 4 of them would be negative 8. So something minus 8 equals negative 1. Get out your calculators. No, it's plus 7. Okay. CrO. So for CrO, oxygen is negative 2, so chromium must be plus 2. So, by the way, the oxidation numbers for Mn is plus 7, and oxygen is negative 2. It's not negative 8. It's negative 2. It's for the individual one. Chromium is plus 2. Oxygen is minus 2. Come on, next one. O2 is O equals 0. Because it's an element at standard state. Oh, diatomics at standard state. Tricky, 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 tricky. Okay, so each oxygen is negative 2. So that means 4 oxygens are negative 8. Each hydrogen is plus 1, so 3 of them is plus 3. So what must phosphorus be? Now, because this doesn't have a charge, then 3 plus something minus 8 equals 0. So that means X equals plus 5, and that is P. Okay. Na2Cr2O7, I already wish I didn't put this on here. So oxygen is negative 2. I'll do it over here. Na2Cr2O7. Each oxygen is negative 2, so that's negative 14. Now I have to decide which one do I like more. Sodium or chromium. Sodium is in column 1, and chromium is somewhere in that no man's land. So I trust the outside more. So each sodium is plus 1, so plus 2. And then plus 2 plus 2x, notice it's 2x, minus 14 equals 0, because this doesn't have a charge. So that means x equals 6, so chromium equals plus 6. Types of reactions help us predict the product, so you should identify the basic types of the reaction. Synthesis, by the way, they have no oxidation number change. So that would be, for example, carbon dioxide gas with calcium oxide. So CO2 plus CaO. And again, I've got gas, so you get the very likely smush of CaCO3. Solid. Decomposition, again, no oxidation number change. So an example of decomposition would be NaHCO3 turns into Na2CO3. Oh, we did this in lab. And H2O and CO2. Okay. So decomposition, the things don't change charge. Now, to show you what I mean by this is calcium. I should have just showed this on this one. Oxygen, each oxygen is negative 2, so I've got minus 6. Calcium over here is plus 2. So carbon would be plus 4. Plus 2 plus 4 minus 6 is 0. Over here, oxygen is minus 2, calcium's plus 2. Notice how the charges are the same. Over here, oxygen is minus 2, carbon is plus 4. Everything is the same charge. Okay? Trust me, the same thing's true in this one. Precipitation has no oxidation number change. So, for example, barium nitrate, BaNO3 taken twice, plus K2SO4 gives the no big surprise BaSO4 solid plus KNO3. And you have to balance them, and their charges will always be the same. So if you check those out, oxygen's going to be minus 2, then you can get the whole thing on there. Redox is a type of reaction where the oxidation number does change. Okay, and that's basically what makes it redox. And the last one is a Lewis acid, where you have a D-block metal, plus a hydroxide or ammonia. So that would be something like cadmium plus 2 plus excess concentrated, OH negative, would give you CdOH taken 4 times, -2. Right? So this is an electron-rich thing, like hydroxide or ammonia. Types of redox. Nitric acid dissolves most metals, not gold, and the products are metal ion and NO. So if I have HNO3 plus, say, copper, I get Cu plus 2 plus NO plus H2O. And this will balance if you try hard enough. But to show you how the charges change, notice how copper's oxidation number over here, Cu's oxidation number is 0. On this side, oxygen is -2. There's -6. This is +1. So this is +5. N equals +5. On the right-hand side, copper is +2. And nitrogen, this is -2, so this is +2. Nitrogen equals +2. So notice how the charge changes. Copper's charge went up. Nitrogen's charge went down. If your charge goes up, what happened is, in the half reaction, the Cu yields Cu plus 2 plus 2 electrons. Okay? So when this happens, the reactant is losing, so this is oxidation. And oxidation is loss of electrons. And then we'll do the next sample one to show you the reduction one, I hope. Iron metal reacts with copper 2 sulfate. So Fe plus Cu plus 2. No, I guess I'll go old school. CuSO4 yields FeSO4 plus Cu. So notice over here, iron's charge element by itself is 0. Here it's in a compound, so it's not 0, -2. And then what do I trust more, iron or sulfur? Well, iron's a transition metal in the middle of the periodic table, so I don't trust it at all. But I'm kind of stuck. Now I do know that sulfate is SO4 -2. So if I know sulfate is SO4 -2, I know iron is +2. Notice how that's cheating a little bit, but hey, it works. That's why I learned my ions. Over here, copper is +2, and over here, copper is by itself, and it's 0. So if I were to write this in half reaction style, I could say, oh, what am I trying to do? I said do the oxidation one, so I want to do the reduction one, so the charge is going to go down. So if I do Cu plus 2, or Cu sulfate, oops, SO4, turns into Cu. Now notice you need the sulfate on the other side, so I'd have to have sulfate. Okay, now these charges are pretty much the same, but notice how this is a -2. Okay, if this is -2, I need to balance the charge by putting 2 electrons over here. So notice how up here I had electrons on the right, that's oxidation. Here I need electrons on the left, so that this side is -2 and this side is -2. So this is reduction. Reduction is gain of electrons. So look right here, we've got oxidation is loss, that's oil. Reduction is gain, that's rig, oil rig, remember that. Methane combusts if I have CH4 plus O2 yields CO2 plus H2O, and fire and heat and spectators. So oxygen is 0 over here because it's an element, and here it's not 0. So you can see it's going to be redox. Come on. Balancing redox, sort of. We don't have to balance it as much as we used to. Now, I got lazy with the charge thing, so I'm going to rewrite this as Fe. And then, so I suppose I'll put it over here. Fe plus 3 yields Fe. Now I need to balance this half reaction. This is my overall. These are my 2 half reactions, and I need the total one. I need to have the charges balance on this. So I'm going to put 3 electrons over here. -3 plus 3 is 0. Cu gives me Cu plus 2, and then I'd need plus 2 electrons here. Notice how my electrons will not cancel because 3 doesn't cancel with 2. So I feel smart in 7th grade and say, that's the least common multiple, and multiply the top by 2 and the bottom by 3 and add them all up. So my reaction would come out to be 2Fe plus 3 plus 3 Cus yields 2Fe plus 3 Cu plus 2s, and most of you would have missed this because you would not have balanced the charge. The charge needs to balance. Notice this side's plus 6, this side's plus 6, and that's balanced. If I give you these two half reactions, which are a bit more annoying, you have to be able to do the same thing. So if I have MnO4 negative yields Mn plus 2, I guess I needed all of this, didn't I? And I give you this half reaction, H positives there, and H2O's here. You have to be able to balance this half reaction. So when this happens, you want to balance your oxygens first. So I have 4 oxygens, put a 4 here. That gives me 8 hydrogens, and now I need to check my charges. This side is plus 7, plus 8, minus 1. This side is plus 2. So I need to add 5 electrons over here. And if I have Fe plus 2 yields Fe plus 3, that would be plus 1 electron. I have to multiply the bottom by 5 to balance the charge. So then I would get 8 H positives plus MnO4 negative plus 5 Fe plus 2s yields Mn plus 2 plus 4 H2O plus 5 Fe plus 3s. Yeah, I don't want to do another one. So types of saturation, quick like, saturated, unsaturated, supersaturated, full, unfull, overfull. And you get overfull by taking a saturated solution and cool it. And you would expect the extra precipitate out, but the extra stays in magically. Woo! Solution, suspension, colloid. Solution, itty bitty particles.
Hey,
how many people fit in the LT stands? Mr. Lovato wants to know. I would say 4,500. 6 of the top 10 biggest high school gyms are in Indiana, though. I know that. Biggest parts are suspensions, and colloids have medium parts. The medium parts have laser beams that you can see through. Normally, if you shine a light through something, you wouldn't be able to see it. Suspension is right there. And that colloid showing that laser beam is the Tyndall effect. Review, blah, 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 blah. Thank God I'm a country boy and didn't do that last part. So, there you go. Tyndall's effect medium for particles, but it's not homogeneous. So that's important. The only homogeneous one is that.